We'll proceed in the usage of Taylor series, and we will see kind of where other places it can be used. Okay, so it is really heavily raining out here, and this is the condition. Probably I can change it quickly. Oh, I thought I could do it, but it looks like it is kind of completely drenched. Okay, so in calculus, we have seen that there is a kind of okay. So in calculus, we saw that the if I have integration, if I have integration, then I have derivation. If I have integration, then I have derivation. If I have integration, I have derivation. What are the uses of derivation? So what are the usage of the derivation? Means derivative, differentiation. So one of the uses of differentiation is polynomial approximation. So if I have a function fx, if I have function fx and there is a function gx, and if I want gx to be exactly copy of fx, if this is fx, okay, fx is any algebraic function, and there is gx being exactly copy of fx, I would say another way to represent fx, if this is fx, then another way to represent it as is gx is nothing but polynomial, only polynomial representation of fx. If this is fx, then only polynomial representation of fx is gx. What is fx? Fx can be mixture of polynomial x to the power n, and then sinusoidal, trigonometric, and then exponential and whatsoever. So if there is fx, then there is gx. Okay, so if there is if there is fx, okay, so if there is fx, then there is gx is polynomial. Now fx has everything. Fx has sinusoidal, exponential, polynomial, but gx is only polynomial. Fx is a black box which has set of algebraic equation, then Gx has only polynomial. Any any algebraic equation can be represented as only set of polynomial? If that is the case, then this is possible. This is shown by Mr. Taylor, that yes, if you have any algebraic function that can be represented fx, then that can be represented as gx, and gx is set of polynomial equation, polynomial representation. If that is true, then now Maclaurin come into the picture, and he's saying yes, indeed it is true. If it is true, then what is polynomial expression of sin x? Sin x is an algebraic equation. Sin x, sinusoidal, sin x is an algebraic equation. If sin x is an algebraic equation, then what is equivalent of sin x as only polynomial, x to the power 1, 0, 2, 3, 4, 5? Then Mr. Maclaurin took the Taylor series, saying that any fx, for any fx, gx is fa at any point x equal to a, fa plus dfx by dx into x minus a divided by factorial of 1 plus d2fx by dx square x minus a whole square divided by factorial of 2 plus so on. fn x by dx to the power n into x minus a to the power n divided by factorial of n. So this is what the Maclaurin, now Maclaurin comes into the picture and he is saying let's consider a as 0. Let's consider a as 0. Now if I want sin x, equivalent of sin x, as if sin x is fx, then what is gx? If sin x is fx, then what is gx? If that is the case, then Maclaurin is saying consider a equal to 0. If that is true, then fa, okay, or consider I want tan x. I believe we have calculated cos x and sin x. Then let's say tan x. So tan of x equal to, that is fx, gx equal to fa plus dfx by dx, by dx. What is derivation of tan x? I don't know. So tan x equal to sin x by cos x. So if I go for derivative, then sine into cos to the power minus 1. If I go by chain rule, then I keep sine x outside and cos minus x would become minus 1 by cos square x into differentiation of cos x is minus sin x. So minus minus cut down and it becomes sine square x divided by cos square x plus, and then the differentiation of sin x is cos x. Cos x by cos x gone. So sine square x by cos square x, sine square x by cos square x, and then plus 1. So that I believe that will become sine square x plus cos square x divided by cos square x. So that will become 1 by cos square x, then sec square x. So derivation of tan x is 1 by cos square x. This is simple. Now gx equal to fa. So tan at 0 is 0. So fa is gone. Next is dfx by dx. So dfx by dx is nothing but 1 by cos square x at x equal to a, at x equal to 0. A is 0. So in that case it becomes 1. 1 minus x, 1 into x by 1. So x. Now plus d2fx by dx square, d2fx by dx square. So it is now dfx by dx is 1 by cos square x. Then what is its derivation? Again, so cos to the power minus 2, then minus 2 outside and 1 by cos to the power 3x. So minus 2 by cos to the power 3x. If that is the case, then at 0, 1, so minus 2. So now it is x minus 2, x square divided by factorial of 2. So minus x square factorial of 2 plus d3fx by dx cube x minus a is 0. So x to the power 3 by factorial of 3. Now I have minus 2 by cos to the power 3x. So it is equivalent as minus 2 cos to the power minus 3x. If I do differentiation, minus 3 would come out, it will become 6 or factorial of 3, looks like. So it would become factorial of 3 and then divide by cos to the power 4x. So it is now 1. So it is factorial of 3 plus factorial of 3x to the power 3 divided by factorial of 3. So 3 gone, x to the power 3 and so on. So if that is the case, then tan x equal to, I believe tan x equal to x minus x square minus x square plus x to the power 3 minus x to the power 4 plus x to the power 5 and something like this. Someone can test it. So this is Maclaurin series. This is amazing in electronics arena also. In electronics, sometimes you need to prove that sinusoidal wave, if I am generating sinusoidal wave through the function generator, prove it, this is nothing but set of square wave. If I take electronic signal as a square wave, if I assemble a square wave, then it becomes sinusoidal wave or sinusoidal wave at particular frequency, pinching at a particular frequency, it would generate a square wave. So these are nothing but these are Maclaurin series only where sin x, tan x, cos x, they are represented as algebraic equation at particular frequency. It will show one particular behavior. Probably we will talk more on it or I'll try to prove it. We will have electronic circuit and then we will prove that sinusoidal wave is nothing but it is set of square wave only. So that we will see. So as I said, the usage of Taylor series, one of them is sinusoidal. We will see in electronics. We have channel for electronic tech owl. So probably it would appear in tech owl also that how sinusoidal is it is nothing but it is set of square wave only. Anyway, now next we proceed that usage example we showed that for the Taylor series, one example we showed that for the first order derivative, if gx equal to fa plus dfx by dx x minus a by factorial of 1. This is first order derivative for the single dimension. For the dual dimension, multivariable gxy equal to fa comma b, because independent variable are two, x and y. So fa comma b plus dfxy by dx into x. I am leaving x minus a into x divided by factorial of 1 plus dfxy by dy into y factorial of 1. So this is first order Taylor series. With the first order Taylor series, we saw that we can calculate algebraic equation for the directional derivative of a function along any vector u. If I have any vector u, then directional derivative of function fx along vector u is nothing but gradient of function fxy, gradient of function fxy dot gradient of function fxy dot and then gradient of function fxy dot product of the vector and then unit vector of u. If I have fxy, I want a partial derivative of fxy or directional derivative of fxy along a vector u, along vector x dfxy by dx, along vector y dfxy by dy, along vector u dfxy by du. That is nothing but gradient vector that is dfxy by dxi plus dfxy by dyj dot product of with unit vector of u. I am actually right. It is that simple. If it is that simple, what about gradient vector? Gradient vector of fx. I mean partial derivative of fx along u vector along I unit vector. If that is true, then gradient vector is dfxy by dxi plus dfxy by dyj. Ij is vector dot product of I vector I. If I do dot product, j vector gone. This is nothing but dfxy by dx. So it proves it. So partial derivative along x-axis is dfxy by dx. It is nothing but directional derivative of fxy along x-axis. Directional derivative of fxy along y-axis, then do dot product with the j, then dfxy by dx will come out, go out, kicked away, and dfxy by dy remains, that is the partial derivative. So this is amazing, and we saw the kind of profit of a company. If we have to calculate the profit of a company where there is a constraint, this is Lagrange way of calculating the constrained profitability. Constrained profitability. But we kind of bypassed Lagrange way. It is complex. You have to calculate two gradients and then do find the value of lambda. Then you have to also see what is the derivative with the lambda and so many. So not required. If you want maxima and minima of for the profitability, if there is a constraint line, then along the constraint line you can calculate the partial derivative. Because if you are calculating maxima or minima, you are actually calculating maxima or minima with respect to x-axis and y-axis only. Everything is along independent variable. Calculus is nothing but game of algebra. Nothing more than that. Algebra is nothing but independent and dependent component. I have a function which calculates sinusoidal. This is not complete. Sinusoidal of what? Sinusoidal of x. Then x is independent variable, and whatever you are calculating is dependent variable. If you are writing a Python function func, and you are passing three parameters and output you are generating, these three parameters are called independent variable in calculus. These independent variables are fed into the function. Function is doing some computation and it is returning a value. That value is dependent variable. The output is dependent variable which is dependent upon three parameters. This is the algebraic way. So if I have kind of if I have to calculate anything, differentiation or integration, it is with respect to some independent component, fx into dx. We are trying to calculate integral of fx along x-axis. dgx by dx, differentiation of gx along independent variable x-axis. If I am looking for profitability of a function fx where there is a constraint line, so if I say dgx by dx, their constraint line is x-axis. dgx by dy is there is a constraint line called y-axis. It's a constraint line. Constraint line means you have to do everything along this line. All the maxima. I have a function called fxy, and fxy is what? Fx equal to x square. I have a function fx equal to x square. If fx equal to x square, then what it is? Then it is equation of a parabola. If it is a parabola, then fx is equal to x square. When x equal to 0, then it is minimum. Otherwise, if x is negative, again x square is positive. So it will come something like this. If I have a parabola, then fx equal to x square is like this. Here it is touching the origin, but both sides it is up. It is global minima. Okay, so it is global minima. If it is global minima, then that's it. So fx, how you found it? Fx equal to x square. If I do single derivative dfxy by dx, then it becomes 2x. Now, wherever it is minima or maxima extreme point, there is no rate of change. If I have this parabola, and if I see this point, if this is x-axis, this point at x equal to this, Here, if I take little bit difference in x, there is a we see difference in y also. If there is a point on x-axis, if I take x at x, whatever is the value in the vertical, if I take little bit right delta x, then there is a change. So dy by dx has some value. But at minima, at this point, there is no rate of change. It is flat. Or maxima, there is no there is a rate of change. That is why it is growing. But there will be a point where it will be stagnant and then it will go downward. At that moment, dy by dx is 0. So if fx equal to x square, then dfx by dx equal to 2x. 2x equal to 0, x equal to 0. So at point x equal to 0, there is no change in the derivative as far as derivative is concerned. It is considered an extrema. Again a derivative. 2x, again d2fx by dx square. Then it is 2. If it is 2, it proves that it is positive. Positive double differentiation means it is global minima, local minima, whatever. Global, local, please see that video. So global minima, local minima. Now this is the kind of scenario that is seen. Can you see this? Two things we will talk. First of all, if someone asks how we calculate maxima or minima, simple. If I have fx equal to x square dfx by dx, that is 2x, 2x equal to 0, x equal to 0. So it is global minima at x equal to 0, d2fx by dx square equal to 2, it is global minima because it is positive. Because everything you are doing with respect to x-axis, did you forget it? If I have, please concentrate here. If I have fx equal to x square, if fx equal to x square, this is x square, this is minus x square. Minus means opposite, that's it. Minus means addition only but opposite. This is x square, then this is minus x square. Consider minus x square and this is x-axis. If this is x-axis, if I say dfx by dx or derivative equal to 0, you are calculating derivative along x-axis. Okay? What about if I have another axis? If this is x-axis, this is y-axis, then there is another axis. What about its derivative along this axis? This is directional derivative. So directional derivative, this maxima minima would differ. It may not be the same what you are calculating along x-axis. Believe it. If I say, if this point I say there is no differentiation, there is no slope, but this is with respect to x-axis. If I have y-axis, then certainly there is a steep slope here. Can you see? If I say there is a slope that is vertical to x-axis, then there is a steep slope. If I say y-axis and there is this is a point, then there is a steep slope. So I cannot say where the derivative is 0, their slope is 0. Derivative with respect to what? Derivative with respect to x-axis means with along x-axis slope is 0. But if I say derivative along any arbitrary axis, then I have to calculate dfx by d that arbitrary axis. So directional derivative means if I say dfx by dx, then that is directional derivative of fx along x-axis. So in Lagrange way, we can call it as constrained derivative dfx by du. This is my way. Lagrange, not Lagrange way. So if I have constraint situation, like we talked about, that company is making profit and profit equal to x to the power 2 by 3 into y to the power 1 by 3. If company is making profit x equal to 2 by 3 and y equal to y into y to the power 1 by 3, when this profitability will be maximum, where x is number of unit of one raw material and y is number of unit of another raw material. provided x plus y equal to, means the total cost should be less than equal to 3 unit. 3 can be 3 million also, where total cost, where x is number of unit for the first raw material, y is number of unit for the next other raw material. If alpha is number of first raw material unit and beta is number of second raw material, then x alpha plus beta y should be less than equal to 3. If alpha and beta we take as 1 1, then x plus y less than equal to 3. X plus y less than equal to 3. If I go for maximum, then x plus y equal to 3. The vector notation is I minus j. X plus y equal to 3. The vector notation for that line is I minus j. If I consider I minus j is another axis, there is x axis that is called I, there is y axis that is called, there is another axis that is I minus j. Unit vector is I minus j divided by square root of 2. That is the unit vector. If I have fxy, then what is the maximum for the fxy or minimum for the fxy along u vector I minus j, not along I or along j. If I say what is fxy maximum along I vector, then dfxy by dx. Along y vector dfxy by dy. Along u vector, that is I minus j divided by square root of 2 dfxy by du. So this I-axis and J-axis, they are nothing but constrained line. This is our philosophy. It's not written in any of the book. So they are constrained line. So if it is constrained line, if it is maxima or minima, then constrained line will become tangent at maxima or minima. But if I say that if I have this as minus x square is the graph and this is x-axis, if I take, it's a vector, right? I is a x-axis means I vector. If it is I vector, if I take it, then it becomes tangent at this extreme point. But if I have another axis, then it is not becoming tangent at this point. Can you see? It is not a tangent. If I take y axis, then certainly it is not a tangent. It is pure vertical. But if I take x axis, then it is tangent at x equal to 0. So maxima and minima, calculating dy by calculating the directional derivative, constraint derivative or partial derivative is along an axis, along a vector. Then it is maxima or minima. It is not any God gifted maxima or minima. So this is what we saw. Now for the single dimension, can we apply? Oh, I'm sorry. So there is another thing. If first derivative I set it to 0, then it is the kind of, if I first derivative, if I set it to 0, then it is extreme point at that point. If I equate it to 0, whatever x comes. But if first derivative along x-axis, that is partial derivative or fx, then it is maxima minima along x-axis. If I take u vector, then it is maxima minima along any u vector. If I calculate double derivative, then it shows me the kind of, it is maxima or minima. But whatever, can you see one? There are two things again here. There is something that is very smart in parabola equation. If y equal to x square, if fx equal to x square, then this parabola has a nature that it has either one global maxima or one global minima. It cannot have double. If I say sinusoidal, then can you see this? This is sinusoidal. Then it is clearly, you can see, if it is sinusoidal, then there is one global maxima, I'm sorry, local maxima, local minima. Then again it will repeat, sinusoidal maxima, minima. There is no global maxima or global minima. Local maxima, local minima, you can calculate in a particular region. But parabola will have only one minima or only one maxima, only one. So if I say parabola equation is y equal to x square, then whatever is the coefficient of x square, that tells that it is maxima or minima. If it is positive, then it is global minima. If it is negative minus x square, then it is global maxima. No need to go for double differentiation or whatever it is. This is the nature of parabolic equation. Okay, anyway, so it is something like we will proceed now. Now, now to tell me one thing, if I have a function fx, if I have a function fx at certain point, this is global maxima or global minima. Can someone try? If I have a function fx, then at some point I know dfxy by dx equal to 0. Anyone would say calculate double differentiation. If you know dfxy by dx equal to 0, then through that you calculate x equal to what? If it is dfx like sine wave, fx equal to sine x, dfxy by dx is cos x, cos x equal to 0, means x equal to pi by 2. At pi by 2, there sine wave at pi by 2, pi by 2 minus pi by 2, 3 pi by 2 minus 3 by pi by 2. At this point, there is extreme point. So if this is sinusoid, if this is sinusoidal wave, then this is pi by 2, this is minus pi by 2, again pi by 2. So if this is the case, because dfx by dx, that is sin x, dfx by dx, that is fx equal to sin x, then dfx by dx equal to cos x. Cos x equal to 0, then x equal to pi by 2, 3 pi by 2, minus pi by 2, minus 3 pi by 2. So there it is extreme point. What is, how I know this extreme point or maxima or minima? So then do double differentiation. Sin x, single derivation, cos x. Sin x, double differentiation minus sin x, single derivative, cos x. Cos x, again derivative is minus sin x. If it is minus sin x, then now let's calculate at pi by 2. It is at pi by 2, sin pi by 2 is 0. So minus 0 means it looks like it is maximum. Okay, then minus pi, then pi by 2, then minus pi by 2. There is also extreme point. So minus sin x. So sin x, sin minus pi by 2 is minus sin pi by 2. Minus cut down, sin pi by 2. Oh, sin pi by 2 is 1, not 0. So first was the double differentiation of sin x is minus sin x. So at pi by 2, it is minus 1. So it is maxima. Minus pi by 2, it is 1. So it is minima. So anyone would say, then calculate the double derivative and you will get the maxima or minima. Okay. Then it is sometimes it is difficult. That we will talk. Then what about if I, okay, someone can get it. If I calculate double derivative, if I have fx equal to very complex equation, logarithmic, exponential, and this and that, and so many. If that is the case, if I go with single derivative, equate it to 0, then I can say at this x point there is a maxima or minima. Okay, at this point, then I have to calculate double derivative, and there are kind of a scenario where it will be complex. At the first go only, can we find that it is, I mean, there can be situation where this is complex. We will see that. Okay, so idea is that can we kind of if fx, if we are doing calculating the if I have a function fx, and consider, I mean, the way we are talking, it looks simple, right? But consider the case of multivariable. We will show it. Consider the case of multiple variable where we have two independent variables, x and y. X and y. If that is a x and y, if that is a complex fxy, then in real life it becomes difficult to think about that it is maxima or minima. If we calculate double differentiation also, how we will calculate double differentiation? You tell me. For single variable, I agree that if I go single derivative and set it to 0, I get extreme point. For those points, if I go for double derivative and set those points, and if I see it comes as positive or negative, I can say it is global maxima or global minima. What about multiple variable case? Multiple variable case, I calculate dfxy by dx, set it to 0, it will have one equation. Dfxy by dy, set it to 0, it will have another equation in x and y, in x and y. If I solve it, probably I'll get set of x and y values where it will be maxima or minima. In multivariable case, there is no line, there is surface. Okay, if there is a surface that I can probably show, if there is a surface, then surface can be like this. Surface can be maxima or minima, because we are calculating dfxy by dx, dfxy by dy, setting it to 0, we solve it and we get x and y point where we can say it is extreme point. How you will find it is maxima or minima? After single derivative, double derivative is not straightforward. d2fxy by dx square, if you calculate, d2fxy by dy square you will calculate, then what you will do? In single variable d2fxy by dx square, set all the x value there for which it was 0 and check it is positive or negative. But in multivariable case, d2fxy by dx, x value you will set, y value you whatever you have got you will set, but what you will get? It is not correlation with the d2fxy by dy square. Now, if you go with d2fxy by dy square and take x square and x and y value, what you got from the first derivative setting at 0, if you set there, then what you will get? It's only d2fxy by dy square. It is not in the correlation with d2fxy by dx square. How to find maxima and minima in the surface in 3D? How to find the extreme points in the surface equation where it is 3D? It is maxima or minima. There, Mr. Taylor comes into the picture again. So, we will solve it for multivariable, then we will go back and we will see that single variable is a special case of multivariable. Two things again, single variable d2fxy by dx square, we know it, but knowing it through a special case of multivariable is separate experience at all. But anyway, there is no way someone can say that my surface extreme point I calculated, my surface, as those extreme points are maxima or minima, not possible. Through algebraic way, not possible. Now, then you have to check the local point. If I know at this x and y it is extreme point, then little left, little right, and around it in a kind of lower contour you have to calculate the point and you have to check that is maxima or minima. But through algebraic way you cannot calculate the way you did for the single variable d2fxy by dx square. That is not possible in multivariable case. So that we will see how to assure that a particular point, extreme point, is maxima or minima. That we will see.